Hi, so welcome to another lecture. Now, this lecture is sort of going to pave the way for the lecture over the next couple of days, where we'll be looking more into the sort of inner workings of operating systems, namely real-time operating systems, and sort of getting used to sort of API or the framework that we'll be using in the labs, which is free RTES, which is an embedded open source real-time operating system. Now, we'll be touching a lot on sort of how tasks, which we'll see in this lecture, are sort of like one of the core portions of like what makes operating systems. Is sort of like this bundling of work or code into a task which can be controlled. Now, we're going to be talking today about scheduling, which is really how you take tasks and run them on a system. But since we're not really going to touch on tasks, this will be more so done tomorrow, but we'll need to know something about scheduling to sort of understand the inner workings of these real-time operating systems. We're sort of in a bit of a, like what came first, chicken or the egg sort of situation. And so for today's lecture, I just quickly want to say, like, just abstract away that we don't really care about what like a task is, in that like we won't talk about how a task is sort of programmed or structured. All you need to know is that a task is a block of work that a system needs to do, and since we're dealing with computers, it's some sort of code, and then these tasks can be controlled. Think of it, they're a nice little package of work, and that these can be distributed or scheduled onto a system, onto a CPU, or onto, these scheduling is not just for CPUs, it can be for communication buses, for hardware accelerators, GPUs and whatnot. And scheduling really exists in any computer system or even other things in life where we have something or some collection of things that need to share some sort of a resource, and how we then best plan them and put them onto this resource while adhering to constraints or respecting deadlines and all this sort of thing. So we'll get into this bit today, but just before we jump into it, you get any questions about like, I don't really understand what a task is, this will be presented or talked about more so tomorrow when we get into sort of talking about like tasks. But today we're sort of interested in just the scheduling of some form of work or some form of abstracted thing onto a resource. And so we're not necessarily talking about code onto computers, onto a CPU, because the whole idea of scheduling can be abstracted to so many other applications. So before we sort of get into it, before we talk about the actual different types of scheduling, really just talking about, in our case, when we're talking about tasks on a CPU, like what we want to achieve is that we have multiple work packets that we can then run on a shared resource. In our case, it would be a CPU. And so in this course, you'll be using a free RTES emulator. So you'll be using a scheduler to schedule your code onto the shared CPU of your computer, right? Now, we want to achieve the result where our program appears that we have created our code, we've partitioned it up into these like work packets that are separate tasks, and they all run simultaneously, like what we observe as simultaneously on our system, right? But what is actually happening is that we have a scheduler which schedules these work packets at different points in time such that they can all get executed by this shared resource. And so how this is achieved is the art of scheduling, and this is done by a scheduler, given scheduling policies and all of this sort of control code or algorithms that make this possible or fit to a certain specification, given a certain application, certain whatever. Yeah? And so really when we want to talk about like scheduling and how we achieve this sort of apparent simultaneous execution, given actual sort of individual executions, is that we need to talk about how these blocks of work are sort of controlled, or the states that they're in, because we have these little packets that we want to then schedule, and so we need a way of controlling what is being run and what's not being run, what we should run, what's next to run. And so we really have to talk about the sort of states that the tasks can be in, that the scheduler can then sort of use as to gauge or to sort of say, yep, okay, this task is ready, I can schedule it now, right? And so we'll then have to talk about release mechanisms, and a release mechanism is sort of the thing that has to happen such that the task is released. And released in this context means it is taken from a state where it's not running, where the task is waiting, to a task where to a state where the task is ready to be scheduled. So we, as people that write the code that dictates sort of these mechanisms, we never put the task into running. This is the job of the scheduler. We are responsible for making sure that we've written the mechanisms that allow these tasks to be put into essentially a list of ready, or into a pool of tasks that are ready for the scheduler, so the scheduler can take interest in them and decide, okay, yep, this task should be the next one. So therefore, this first point here sort of emphasizes this, that we want the scheduler only picks tasks that are in this ready state. And so these states are there's actually another one that we'll come to, which is suspended. But as far as actually running tasks are concerned, tasks that are active on the system, they can be essentially in 3 states. And this release mechanism is the mechanism or the condition by which the task is put from a block state where it's not running, it's waiting for something, it's waiting for its release, to go into this ready state where it can be then put onto the scheduler, onto the CPU or the shared resource by the scheduler, meaning that the ready state is the pool of tasks that are of interest to the scheduler. When the scheduler then chooses one of these tasks, it will then put it into the running state, meaning it is scheduling it onto this shared resource, the CPU, or whatever it is that we are scheduling for. When some, maybe it's completed, but this can also be because of other things. When some event occurs, you can then also have events that put it into the block state. And so we'll see this coming up, what this sort of means. But there's 2 main types of release mechanisms when we're talking about scheduling. And this is also very important when we're dealing with real-time operating systems, or the whole, this course is sort of named after real-time. And so this means that we're dealing with, essentially, we're really concentrated on time and what time means, because time is not always inherently available or part of a system. When you're talking about a Game Boy or something, some basic computer system, it doesn't have an inherent concept of time. So it's just going to try and achieve its frame rate, or just sort of execute the code that's on the cartridge, but it's not actually doing it in some sort of regard to the external environment, meaning the time. It has a CPU clock and it just executes its instruction. But what we are actually interested in a lot of cases is that we want things to happen in relation to the wall, the clock on the wall, in real time. And so therefore we have this important sort of release mechanism that is time triggered, meaning that some things are released at specific points in time. And so this is usually a periodic can be helped to achieve periodic things, such as frame reaching an FPS. Now this Game Boy might also reach 10 FPS or whatever, but it's not so much a desire for it to actually achieve a certain time, a periodicity in time, as much as it is just the hardware's capabilities. And so when we actually want to achieve with a high-powered system that could, for instance, run at 200 FPS, but we say we want to achieve 50 FPS, then we need to set periodic release schemes such that we achieve this time-aware releasing of our tasks to achieve our constraints or the goals of our system, right? So this is one very important and common release mechanism that you'll find in real-time operating systems, because we have this ability to use time to our advantage. What is more common on, let's say, a wider range of systems, meaning essentially pretty much any computer systems that have interrupts and this sort of event handling capability are event triggered. Now, event triggers, not so much in terms of time. They are more in response to some sort of an interrupt or some sort of a signal that is present or then made present on the system. Meaning, for those of you who have not really got any experience with it, an interrupt is a signal sent to the CPU to interrupt its execution when some sort of event happens, and this could be, for instance, the pressing of a button connected to some embedded system, where the pressing of the button will trigger a GPIO, like a general purpose input-output pin, a GPIO interrupt, which will then send a signal to the CPU that interrupts it and triggers, for instance, an event. And this event could then be passed through to the scheduler, which is then going to sort of use this event to release tasks or what have you. Tasks that are have been coupled to the happening of this event for its sort of releasing, right? And so these are generally based on interrupts because interrupts are a very prominent way of sensing events. You can, for instance, have software events. This is also, as we'll see, is the entire basis of the free RTOS emulator, which we'll be using, as it's essentially all emulated. We don't really have any hardware interrupts coming in. This whole thing has been emulated using software interrupts. But on basic systems and more commonly on embedded systems, it's very common that you'll offload this sort of checking for events to the hardware, because if you have, a good example of this is checking if a button has been pressed. You can either with code check if the button has been pressed, which is what we call polling, and so this is like you'd use maybe a time triggered event to actually check the button in a periodic manner, and then if the button has been pressed, you would then say, okay, cool, this event has happened, we can do things. But the disadvantage is that you have to spend the time, like your CPU is spending clock cycles, to actually execute this checking code. So on an embedded systems, what is commonly done is you avoid actually having this overhead or actually having to execute this code for checking by enabling the peripherals or setting up the peripherals, namely the GPIO controller, so the actual piece of hardware on your microcontroller that controls the GPIO pins. You can configure this in a way that it will send a hardware signal to the CPU every time or when a certain button is pressed, when it's released or pressed. These things are all configurable. And this means that the CPU is not actually having to wake up and check the GPIO. It just keeps doing its thing until this interrupt signal arrives and it interrupts the execution. So without going into too much detail about what happens here, we'll see a bit more detail in the coming lectures. It essentially just says, it just pauses the CPU, whatever it's currently doing, and it executes some predefined code that you can write. And so in there we can put event handlers or whatever. Okay? So these are the two sort of common release mechanisms that you'll find. And we're going to be very interested in time triggered because we actually won't have embedded hardware to deal with, like in our hands for this course. So we're not going to have really that much event triggered. We'll use software events in our emulator, but these are not so much interrupts as they are waiting for a certain message to be sent, which is still an event, but it's not an interrupt-based event. It's a software message, so it's a sort of software interrupt, if you will. Now, when we're talking about scheduling policies, we need ways to determine the order in which our tasks are being scheduled onto a system, so onto a CPU. The order of which the tasks are executed is essentially the schedule that the scheduler is determining. Now, there's two sorts of ways that we can determine this sort of order of task execution, namely which task is allowed to run and when. And we can do this either statically or dynamically. And as the names sort of give away, a static scheduling policy or a static schedule is a way that we predetermine when tasks are going to be run. And so static scheduling is extremely common with like safety critical and just critical systems where we want to be able to do an offline analysis and statically determine and evaluate the scheduling sort of order that we ensure that we're going to meet our deadlines and our system is going to be stable, and just because we can't afford to have any mistakes, right? And so this sort of static schedule can extend to the sort of communication buses, or just to scheduling, for instance, when sort of IPCs, like inter-process communications, or just in general messages are sent. And it's and the static schedule fits very well with time-triggered releases, because we want to be able to do a static analysis in terms of task execution times. And so this is when this scheduling ties in with worst-case execution time, which we will also see later in this course, when we can do a sort of a scheduling analysis based off of the time triggering and the time and the execution times of tasks, to sort of perform an evaluation or a validation of our scheduling, a set of schedule, our task schedule, to make sure that we adhere to the deadlines and the constraints of our system. So this is why a static schedule is very well fits with time-based release schemes. It's also very common on bus systems such as Ethernet and CAN bus, and this uses what's called, very commonly called, a scheduling type called time division multiple access, which we'll touch on briefly in this lecture. So this is one type of scheduling which we very commonly see on safety critical and sort of embedded systems, generally systems that are not, let's say, as complex as like our laptops, which where, I mean, you can, if you think in terms of complexity, my laptop can execute so many different types of software. I can go onto the internet and download 1,000 different programs, and so therefore we can't do sort of this static analysis of all the different programs I might open or whatever. And so we need a way for scheduling all of these different programs that I'm executing onto my CPU that is able to handle all of the different sort of tasks that I might start or stop or whatever, because the system is in that way a lot more complex. We don't know when I install my operating system on my computer, I don't know all the programs I'm going to be running and when. And so these sort of more like flexible systems would use a scheduling known as dynamic scheduling. And so what this is that during runtime, meaning while the system is running, the scheduler is actually on the fly determining which task should be run next. And so it's sort of a way of you're setting up the system's code such that you just set the tasks into there. You're handling sort of the release mechanisms, but the scheduler will on the fly determine, it'll pick one of these tasks and put it onto the CPU, rather than just following some predefined order that has been specified at compile time, meaning when the system was actually sort of created in a way. It does this sort of dynamic checking and releasing of tasks based off of dynamic events or dynamic timings. And so this is a much more common sort of scheduling scheme when we're dealing with systems like general purpose operating systems, Linux and Windows and Mac, or in terms of our laptops, or when we're talking about not so safety critical systems such as game controllers and sort of like a Game Boy and whatnot. These systems don't need to be evaluated to the degree of the systems, of critical systems, where we will probably want a static analysis to guarantee, because static analysis will guarantee us that our scheduling deadlines are being met. And so these sort of systems using static analysis, static schedules, are probably the systems that you'd find in aeroplanes and whatnot, in these very critical situations, whereas you'll find dynamic systems more commonly in like less critical embedded systems, right? So then we sort of come to another defining sort of property of scheduling. So we've covered sort of the release mechanisms, and then we sort of say we split scheduling types into static and dynamic, and we can split them, or we can essentially split it. split these policy or the types of scheduling or the characteristics of a system again into two different types, and this is preemptive and non-preemptive. And what this is, it's a characteristic of the scheduling policy or the scheduler that allows the temporary interruption of an executing task with another task. Now, this is done in a way that when a task is running, it can be interrupted with the execution of another task with the intention that the task that was interrupted will be finished at a later point in time. So not that it will be just thrown away and never executed again, but this is very important when we're dealing with sort of tasks that have different priorities, which we'll touch on soon. It says that, okay, if I have a really not important thing running and something important needs to get done, I'll do the important thing first and then go back to the unimportant thing. Sort of like how we as humans operate, in that we might stop doing something that's not very important, and then you'll go and do something more important, but you will come back and finish your work later on this less important thing. And so this is this preemption, and what preemption means. It means that the system will be, it will allow for this interruption. Now, it does this in a way where the scheduler is deciding what is going to be done and when. So the task itself doesn't have any say in this. The task can't say, I'm a low priority, but no, I really want to finish. If it was meant to be finished, then it should have been given a high priority by like the person designing the system, or by the scheduler, which can also sort of change the priority of task, as is very common in general purpose operating systems such as like my Linux laptop, where the scheduler can actually, or the operating system itself dynamically changes priorities of tasks based off of certain metrics and timings, right? But the task itself is not actually responsible for its own scheduling. This is why we centralize this control of tasks to the scheduler, as this last point says. So in contrast to this, we have what is known as like non-preemptive tasks. And as you can imagine, this just means that we cannot interrupt the execution of current tasks. And so as you can imagine, once a task is set to run, it will run until it is finished, until completion. And so there's advantages of this, and there's obviously strong disadvantages. It means that the scheduling policy is quite easy to implement. We don't have to worry about other tasks sort of interrupting, because once we have multiple priority levels on a preemptive system, you can get quite complex execution patterns on your system, because all the possible preemption possibilities and things. And so then doing some sort of advanced scheduling analysis of such systems can be very complex. On a non-preemptive system, we don't have this. And it's also very common that you'll see non-preemptive systems in critical applications again, because of their sort of simplicity, and the simplicity leads to very you can validate these systems very easily and be very precise about your validations. So the advantage is that they're easy and simple in a way, and they don't have much overhead, meaning that when a task is preempted, there is overhead in actually swapping the tasks from running from one to the other, which we'll cover in the upcoming operating system lecture where we talk about context switching. But you can't just swap one task to the other on the CPU without some sort of overhead. And so by not having this swap, we obviously don't have the overhead of doing this, and therefore we have this low overhead advantage of a non-preemptive system. Disadvantages is that if we have a system with multiple priorities, the higher priority tasks will have to wait for these lower priority tasks to finish execution. And so therefore we can actually incur very large delays of high priority tasks as a result of lower priority tasks, which can be undesirable. But this is obviously all you choose these sort of properties of your system, preemptive, non-preemptive, given whether it actually fits to your application that you're going to want to implement. Now, a problem that we'll get sort of like why it can be counterintuitive that non-preemptive is also sort of difficult to analyze is that a non-preemptive system means that you need to know how long your tasks are executing for, so that you can't say your low priority task can highly impact your high priority task because it can't be interrupted, meaning that to know when your high priority task would finish after the low priority task has finished executing, you need to have very accurate estimations of the execution time of your tasks. And so this is a thing that we'll touch on when we're looking at worst case execution time analysis, but determining how long tasks can take to run until completion can be very challenging. And so by having this sort of requirement that you now need to know the execution time of your tasks, this makes the global analysis, meaning the entire systems analysis, very challenging, even though the actual scheduling policy, should you know these times, or analysis with these times is very simple, right? That being said, also, I mean, sort of going hand in hand with this sort of ability to not interrupt low priority tasks, it will lead to less responsive systems, because let's say that you have some sort of some sort of irrelevant task that runs a lot of the time, but when some sort of a button press happens, it'll trigger a high priority task. This high priority task has to wait for this low priority task to sort of finish, meaning that you'll find a delay between, for instance, a button press and when the task actually runs, so when the response from the system happens. And so this is why you can find this sort of decrease in responsiveness from the system. Non-preemptive is extremely common in communication protocols. As you can imagine, they sort of work on the precipice that communication packets or something shouldn't necessarily be interrupted. I mean, you want to send all of your data before you sort of schedule the next sending of some other data. And then, for instance, also this last one, this is also unsuitable when the execution times of one task are longer than the deadlines of another task, meaning that should this other task who takes longer to execute happen before the other one, then the other task is guaranteed to not meet its deadline, meaning that this is not suitable. So, moving to this figure, we can see a sort of an example of the two. So let's say we have these two processes, and the length of their little blocks is how long they take to execute. And so in this case, we're lucky we know the length. I mean, we're given a length, which is nice. And so on a non-preemptive system, this means that we cannot interrupt the execution of the current task with the next task. So in this system, we can see that P1, process 1, has a higher priority than process 2, meaning that the scheduler will opt to pick P1 to execute over P2. So as we can see here, on a non-preemptive system, or actually on both systems, we'll initially start with running process 1 because it's a higher priority. And so on both systems, process 1 will run because of its high priority. It will finish its completion because it can't be, even on a preemptive system, there's nothing to interrupt it with a higher priority. So this will be the same. Then obviously there's nothing running the system. The process 1 will spawn again or be released again, and then we'll see it executing again. But where these systems sort of differ is when we get to this point in time, when process 2 wants to start executing, it will be able to execute the first portion of its process normally, because there's nothing else running on the CPU. But now, on a preemptive system, at this point in time here, process 1 has been released, and since it has a higher priority, the scheduler is going to preempt the execution of process 2 and run process 1. So in this case here, we'll see that process 1 then runs, and this delays the completion of process 2 because it's sort of been interrupted in the middle and missed out on this chunk of execution time. And you can see here that the process 2's execution has been shifted back in time. Whereas on a non-preemptive system, this interruption cannot happen, and therefore process 2 finishes completing, and then process 1 is scheduled on. And so this is the big difference, is this preemption here prioritizes or allows for high priority tasks to run in a more responsive manner. So I was mentioning actually here that they have priorities, and now let's go a bit more into depth on them. Now the priority of a task or a process is the metric or the value by which the importance is, as the name sort of implies, priority, the importance of a task is quantified. And this is the value that the scheduler uses to make its decisions. So then there's essentially multiple ways of sort of choosing a priority in a scheduling policy, and that you can maybe use no priority. They'll be used sort of like in in scheduling processes or scheduling policies where tasks are not scheduled according to priority. There can be other sort of things that are used to determine scheduling order. This is very common in static schedules where someone or something manually decides the order, and necessarily by a priority, but it actually determines the order in which things execute, or in common in scheduling policies where you don't so much deal with the importance so much as you deal with just when they are made ready. So when tasks unblock, the first one to release gets run, essentially. So this is a sort of first come, first served method, right? Opposed to that, you can also sort of have a scheduling policy which is very common in sort of some systems where it tries to be fair in that it will allocate equal amount of time to each policy, process. You can also find sort of mixes between this sort of round robin and priority-based scheduling, which you'll find common on general operating systems, where the CPU doesn't really differentiate between like the programs running. It wants to try and be fair between both of them, and the more time that one process takes, the sort of more time is distributed to the other tasks to try and keep it fair, which we'll sort of touch on a bit later in this lecture. But the most sort of important ones to us are sort of this fixed priority and dynamic priority, meaning that a fixed priority is essentially sort of goes hand in hand with this sort of static analysis, in that at design time we actually allocate a priority to each task. And so one thing that we'll be dealing with in free RTES during the labs of this session, while we can change the priorities, for most of our applications or purposes, we'll be implementing fixed priorities, meaning that we'll create processes and we'll set at design time, like when we're writing our code, we'll give these processes their priorities. And so this just means that the sort of, you can do a somewhat of an easier static analysis because you don't have to think so much about priorities changing. A good example of this is actually sort of rate monotonic, which is very common and which we'll be using in the examples and sort of like the exam questions, where the task duration that it takes to execute is actually what is used to give it its priority, meaning we want to execute the shortest tasks. The shortest task we execute first. So we're interested in getting as many small things done as possible, and we put off the long sort of hard work until the end by giving it a lower priority. Dynamic priorities is, as the name sort of implies, it's given that a priority of a task can change during the execution of the program or the runtime, right? And so this is very common on like systems such as like general purpose operating systems, where if a task where the task is trying, the schedule is trying to do this sort of round robin to be fair sort of thing, meaning that it might change the priority of processes if they're not getting CPU time. So it'll sort of dynamically make them more important so that they don't get starved of CPU time and get executed. And so dynamic priorities work really well with sort of schedulers that are trying to be fair to others. And this can also be really sort of useful when you're trying to do sort of really fair scheduling, where you want to make sure that you're not sort of, depending on the shared resources that a task is holding, you might want to sort of make sure that you can avoid tricky situations where, I don't want to explain this now. This priority inheritance will go into depth about this in the next lecture, so I'm sort of just going to leave that there without having to explain this. This is somewhat of a complex topic without going into too much depth twice. So I think we'll look at some sort of common dynamic or scheduling strategies, which we'll be then using for sort of doing some scheduling analysis in this course, or mainly for giving you the tutorials and also in the exam. So the first policy that we'll look at is first come, first served. And so the name pretty much gives away everything, in that you have some sort of a queue, and the scheduler keeps track of sort of like this queue, and when a task is released, meaning it is made ready for the scheduler to actually choose to schedule it, they're just put into this first in, first out queue, meaning the first ones that come in are the first ones to actually get scheduled by the scheduler, right? And so then when a task completes, the scheduler simply just picks the next one in the queue, and this task that's completed will then at some point be released and be put back into the end of the queue, and then it will sort of make its way through to the front. In this way, it is a non-preemptive sort of system, because it's just waiting until the task finishes and it picks the next one. Wait until the next one, the task finishes, and picks the next one, right? Now, why it's the dynamic scheduling is that we can actually have sort of multiple queues, and that these can be sort of changed, like there are different priorities, and therefore we have this sort of dynamic scheduling that can be resulting. The queues themselves are given different priorities, but the tasks themselves aren't so much given priorities, because they just sort of go into these queues and then get popped off the end, and they just sort of sit in their queue, while there can be different different priority queues. And so this is why we have this sort of dynamic scheduling resulting from this. So this is very simple. I mean, this is the sort of the scheduling policy used by FreeRTES, which you'll be all exposed to throughout the period, the duration of this course. And how FreeRTES works is that you allocate a task a priority. Now, counterintuitively to this point here, it does have a priority, but what actually is happening is that it just, by giving it a priority, you're telling it which queue it should be put into. And so the tasks in FreeRTES work in this way, in that you set it a priority, and it's just telling the operating system which one of these queues should get put into. And so as you can imagine, when FreeRTES, the scheduler, is running, it just picks the highest priority queue, pops all the tasks out of it, and then when that one's finished, it'll just go to the next queue, pop out of the task for it, and then as those tasks finish, they go back into the end of their queues, and it just keeps going, right? It'll just step its way from the highest priority queue, run them until the queue's empty, next priority queue, run them until the queue's empty. And so this is sort of what we can see here. Now, just to go through this sort of example a little bit, and also to maybe sort of clear up some confusion about the non-preemptive. When we're talking about non-preemptive, we're talking about inside of each queue, meaning that the next task in the queue can't interrupt the task that was popped off the end of the queue and is currently executing. But what we see in FreeRTES, the scheduler is preemptive, but it means that a higher priority queue can interrupt a lower priority queue of tasks. So in that way, that we do get preemption of like higher priority tasks, of lower priority tasks with higher priority tasks, but within the same sort of priority level, meaning the same queue, we don't actually we don't have preemptive behavior. So in that case, this first in come first serve is non-preemptive as long as you're dealing with a single queue, right? So within each queue. And then this is what you'll see here, that we see the process 1 was created first, let's say, and then this one was created second. And so in the first come first served, this is the sort of execution pattern that you'd have. It's just simply this one runs first, and then it gets put back into the queue so it's ready to run, and then this is the sort of resulting scheduling pattern, right? So moving on to like another very common scheduling strategy, we have round robin. And so what this means is that the release tasks are put into a first in first out queue, and then the scheduler just picks the first task to run, but the whole idea of round robin is that it's trying to be fair to the tasks. So what happened, the only difference to the previous one, we have this first in come first served, which round robin is in a way, meaning that they both use first FIFO queues. The only difference is that after a fixed amount of time, which we will call a quantum, the current task is then blocked such that, and then put in the back of the queue such that the next task in the queue can be released and scheduled. And so all of this tries to do is tries to make it very fair. So there's no, just by sort of making sure that we're not going to let long tasks run for like a long period of time, we'll sort of we'll cut off the block of time and give the CPU to the next task, and the one that was blocked can then return to the end of the queue, and it just sort of works in sort of repetitive fashion. So if we take the same example and we can sort of break it up into these quantums, meaning quantum for us is this block you can see here. If we run this example then using round robin, we would see that this task would get put into the front of the queue, but it would only be allowed to execute for this one quantum, meaning this block here. Then this one would execute for one quantum. And so this guy would be returned to the back of the queue with still one quantum of execution to be done. And after he's finished executing his quantum, he would still have this 1 and like a half quantums left, right? So then The second block would be executed after he goes back into the end of the queue, but then here we get both of them executing because at this point in time here, where the dotted line is, there's actually not anything left in the queue except for itself, so it will just continue executing, right? But then as soon as this guy gets put back into the queue, so once this quantum is sort of like the schedule is invoked here because there's nothing left to do, like a manual sort of invoking of the scheduler, this guy is in the queue again, and so we can schedule him on for one quantum, and then obviously the process 2 is not available in the scheduler at the end of this quantum, so it'll just keep executing. So this is a sort of this fairness approach to scheduling with round robin and a FIFO queue. Okay, so just have to get my jacket again. It's a bit cold, unlike in Singapore. Now the next one we're going to look at is rate monotonic schedule. And now we'll be using this a lot in the examples. It's pretty simple, as I sort of mentioned it briefly before, but it works on generating fixed priorities, but these priorities are based off of the task's period, meaning not so much the execution time, but how often they happen. So as we can see here, the period of these tasks would be between like this execution, like starting the process 1, and when it wants to start again and again. So these dashed lines here, this represents the period. And as we can see, the period of process 1 is shorter than the period of process 2. Process 2 starting here and starting here again. Therefore, process 1 is given a higher priority than process 2. And the whole idea of this is that the more frequent tasks need to be run more commonly. Therefore, we should try and schedule them first, because there's a higher chance that if we schedule them first, we'll meet all of our deadlines. And so this is also done in a preemptive way, in that we want to try and put as much focus on running these short, these sort of high frequency tasks to guarantee that we're meeting as many deadlines as possible. And so if we look at the actual scheduling sort of these two tasks here, we can see it's preemptive, meaning that process 2 could be preempted by process 1, which we see, for instance, here. But process 1 will run first because it's the higher priority, because it's got a shorter period. Process 2 will then run, and it will run until this point in time when process 1 is released again. And because process 2 hasn't actually finished executing in time, it will get preempted. And this is this chunk here that sort of gets delayed because of the preemption and sort of the execution of this higher priority task 1, because of its shorter period. And so the shorter the period, the higher the priority. And this is sort of like the whole concept of it. The period just determines the priorities, and then it's just a standard sort of preemptive schedule, right? Similarly to sort of this rate monotonic, we have another scheduling strategy where it's based off of the timing of the tasks. And so this is, as the name quite simply says, that we take the deadline of the task. So this is not so much the period or the duration of the task, but each task is given a deadline that it should meet. And so it's not really shown on this. I mean, in this case, we can take the deadline. There could be a deadline that falls sort of somewhere here, meaning like we can say this task has a period of blah, 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 but a deadline that is not necessarily the period of the task. But in this case, the period of the process 1 is that it should execute before the period of the next task happens. I mean, before the next task starts executing. And so the priority schedule is determined dynamically given how far away is the actual period of the current task execution. Because as you can imagine, as time sort of ticks by, these periods or these deadlines change in which is actually the closest, so that the priority schedule or the priorities of the task can dynamically change as well. So this is then also used as a preemptive system, because if given that the priorities of the task change such that the next deadline is made the highest, this actually leads to a very optimal schedule that if a task set, I mean, we can sort of say that given the task set, it will be schedulable at all if at all schedulable, it will be schedulable with earliest deadline first, because earliest deadline first focuses on, exactly as the name says, reaching the next deadline putting that as its top priority, which makes sense in that it's working 100% to try and meet all of its deadlines. So this is sort of how it would look, in that we'll at this point in time, the deadline of this task is the closest, and so it's going to execute this until it's finished. Then process 2 is going to run, and when we get to this point in time, we can actually see that this process here, its deadline is back here, meaning that the processes 2 deadline is actually closer, and so that's why we do not get a preemption here, unlike in rate monotonic, because it's a dynamic priority schedule, unlike rate monotonic, which is a fixed priority schedule. That meaning at this point in time, that the priority of process 2 has been made higher than the priority of process 1. And if we keep stepping through it, when this task finishes executing here, we then start running process 1, because it's the only task that's actually been released and ready. But then when we get to this point in time here, there's nothing on the CPU, so then we'll run process 2. But if we think about it, this point in time, we'll have, or as even better, we'll look at this point in time here. This task is released, but its deadline is closer than the priority than task 2's deadline. Therefore, this process 1 is actually made to have a higher priority, and therefore it will preempt process 2. And so hopefully this should be made clear why we have this sort of scheduling order that we can see in the bottom of this slide. So now while we've looked at all of these different sort of scheduling schemes, we're going to look at scheduling analysis, and we're going to look at, or schedulability analysis, and namely we're going to look at rate monotonic, because it's going to be of particular interest to us. So what schedulability analysis aims to achieve is that given a set of tasks, we want to determine if this set of tasks is schedulable or not, meaning is there some order of the tasks that can be created such that every task will meet its deadline and we won't have any voided deadlines. And so this is obviously very important, this sort of performing schedulability analysis in critical systems where we can't have any deadlines not being met, and such systems are known as hard real-time systems, which we'll talk about in the coming lecture. So to do a schedulability analysis, we have to sort of define a set of variables that we're interested in. And so every task gets given a period. So this is sort of, as we can see here, the time between when the task is actually released. So this is what we call the inter-arrival time, the minimum amount of time between 2 task executions. So without delays, like what was the minimum amount of time between 2 task executions. The execution time, which is of course the duration of the task that it would take to run on the CPU. The priority, and so in rate monotonic, as we can go back to here, this is determined by the period of the task. So between 2 executions of the task, the shorter the period, the higher the priority. And so this is what this stands for and how it's determined. Now the deadline of the task, this can be based on, set just as a the sort of the release time of the task plus some time, or it can be maybe it needs to be finished before the next occurrence of the task, but it is some point in time that is considered that should be met for the task to be successfully executed and for the system to be schedulable, right? Now the response time is essentially the time it takes for the task to finish executing from when it was released, given not just sort of like executing time, but there could be delays that are invoked or generated from other tasks preempting it. And the response time is sort of the maximum amount of time that can be possibly observed from when the task is released to when it's finished executing, taking into account other delays that can happen on the system. And so this we'll see as well when we're talking about worst case response time and execution time. This response time is sort of where we have to do an analysis of not just so much of the single task, but the collection of tasks and the delays that they actually sort of impose on other tasks. So now, in this evaluation, or in our schedulability analysis, because we haven't specified the deadlines, we are essentially sort of making the assumption the deadline is the period sort of divided by the release time, the minimum inter-arrival time, right? So then to make a system, or to sort of say that a system is schedulable, there's a couple of sort of things that we can think about, right? The system utilization, meaning that it needs to be between 0 and 1, as the system can't be more like 100% utilization means there's a utilization of 1, and therefore we can't have a system that is utilizing more than 100% of the system's resources. So the system utilization must be less than or equal to 1 for a system to be schedulable. Similarly, we have to say that the response time of each task has to be less than or equal to the deadline. So this is a necessary and a sufficient condition to say it is schedulable, whereas saying that utilization is less than 1 is not necessarily sufficient, because given preemption or the order of the task, we might miss deadlines, even though we are not we're not actually exceeding the 100% utilization of the processor. Sorry, distracted by my email. So therefore, we need to sort of determine in a couple of steps. We can say, hey, we need to make sure that this is met, but this is not actually enough for us to say, okay, I am completely convinced that that this is schedulable. But if you go and you prove this sort of condition here, we can then prove sufficiently that the system is schedulable. And so generally, the schedulability analysis, we do this sort of making sure that the utilization is less than 1. And it's sort of like a quicker check. It's easy to calculate, and it's a quick check to see essentially if it's not schedulable. So if we hit more than 1, then we say, okay, it's not schedulable, end of analysis. If we hit less than 1, then we're like, okay, it might be schedulable. Let's continue on and check and see if the response time of every task is actually less than its deadline. Because if we've reached this condition for all tasks, then we know that we have a schedulable system. And so this is sort of the process we go through of doing this sort of quick initial check to make sure it is potentially schedulable, and then we sort of do this more extended check to say, yep, definitely schedulable. So then this first test of ours that we want to check, is the processor utilization less than 1? Meaning, are we exceeding or are we not exceeding the resources that we have available? And this is quite simple, really. I mean, we just want to take the sum, so of all tasks, and we see we have the execution time, so the amount of time it takes to actually execute on the processor, divided by its period. And so this just tells us essentially the utilization that the single task is creating. And as long as the sum of this is less than 1, then we may be schedulable. If it's greater than 1, we are definitely not schedulable. But if it is less than 1, then we may be schedulable, and we need to go on to essentially the second step, which we'll see here, right? And so this is sort of like the first quick test that we're going to do, or you will be doing in a schedulability analysis. So if you do get this satisfied, meaning that you've summed up all of the execution times over the period, so essentially creating, sort of looking at the load that this task is creating, if this holds true, then we'll move on to the second test, which was developed by Liu and Leyland in 1973. And essentially it's for rate monotonic scheduling, and it will determine that the task set is schedulable, right? And so this test, really what it does is it's just sort of so their test put forward that for some n number of periodic tasks, meaning that they have a period that is always the same, because you do obviously have tasks that are non-periodic. So that for this set of periodic tasks, if you look again at the utilization, so different to this here, where we say, okay, we want to take the sum of the execution times over the periods. If this is less than this here, so essentially the number of tasks by 2 to the 1 over the number of tasks minus 1, if this is satisfied, and then you say, yes, my task set is schedulable. But if it's not, then you have, again, to continue on and say, okay, it could be schedulable, but I have to do more investigation. And so if we look a little more at where this came from, where's my mouse, what's happening? Sorry, computer is struggling. Hello. don't know what's going on. So if we look at this formula that they put forward, and we take the limit of it, saying that the limit being that we take an increase, like an infinite set of tasks, like an infinite number of tasks, what it's really saying is that as the number of tasks goes to infinity, we sort of end up with this 69% utilization, right? And so what they're trying to say is that they are essentially, they're guaranteeing that as long as we sort of sit below 96.3, that we can, or that they've estimated that any set of tasks can meet their deadlines. But obviously, if you exceed the 69.3, this means that this is sort of this no, it still might be schedulable, because really, as long as any task set is less than 1, it may be schedulable and we need to do further analysis. But it's sort of saying if our sum of utilization is less than 69.32, then then the deadline should be able to be met on a preemptive rate monotonic system. But then we have this problem that this may be schedulable if we fail this, and if we fail this, or if we meet this condition, we may be schedulable. Now, how do we need to sort of say without doubt, okay, I want to see if my system is schedulable. It might have a utilization of 100%. So how can I test then that it is then schedulable? And so this is when we get to our third test, which is we're going to use a fixed point computation. And so a fixed point computation is essentially saying, okay, I have a function where a value in a function's input domain is mapped to itself via the function. And so this might be a bit confusing, but essentially what it's saying is that the input to a function here, for instance, C, actually creates the output C, and so you can essentially loop this function until you reach a steady state, because at some point f of C will give you the same C value that you fed into f of C, and so this would always equal the same thing. And this is sort of what we're wanting to do. We're essentially going to feed the input into our sort of this function to determine the response time until we get the same input again on the output. Therefore, we know that we've sort of hit this steady state response time. And then, I mean, if you were to plot this sort of the steady state that we would reach, that means essentially that once you feed this sort of result, C, back into the function f of C, you would get this coordinate C f of C that lies on the line xy, so essentially just a 45-degree line. And so the problem that we have is that this sort of like this interruption number, or the number of the response time, depends on how other tasks are interrupting it, and the number of these interruptions depend on the response time. Okay, and so this is sort of like one depends on the other, and therefore it's a non-linear problem. And so what we can do is we sort of essentially keep solving this problem until we reach a steady state. And then this steady state is what tells us our response time. So essentially we want to find the steady state response time for every task, and then we can know if the response time for each task is less than its deadline, and if so, we're good, we're schedulable. And so to put that sort of problem formulation onto paper, this is what we end up with. And we're saying that the response time is given by the execution time of the task added to the sum of all higher priority tasks. So this is essentially, we're just taking this sum of this here for this here, this is the conditional for our entire test, but we want to take the sum of the higher priority tasks where we look at the response time of the task over the period by the execution time of the high priority task. And so this might be a bit confusing or not really make sense, but we'll see in an example what this actually aims to achieve. And so now we have our essentially the formulation of how the response time is calculated. And we think about this sort of logically, we have the actual execution time the task will take, plus the sum of the response times, or the sort of the possible delays that we can incur, meaning this is the execution time, times by the sort of the portion of the time, the CPU time that this task will run, So this is the execution time plus the possible delays here of all higher priority tasks, and this will give us our response time. So we think about it in this way, this is the sum of, this sum generates the possible delays that we can incur, plus of course the time that it takes to actually execute. And so how we need to calculate this is that the response time, or sort of like the response time of our task, could be changing. And so this is this sort of problem that we run into, that the response time impacts the number of interruptions. And so the number of interruptions, where was it? The number of interruptions depends on the response time. This is like loop. And so now what we're going to do is we're going to sort of essentially solve this in a fixed point way, meaning that we solve this iteratively until the result that we get out is the same as the, so essentially this is our result, and if we feed this result into the next iteration here, then we'll eventually end up with a steady state result, and this will be what we'll take as our response time. So if we go through this here, we can then actually sort of phrase this formula for the, to do a fixed point computation where the response time n takes in the response time n minus 1, so from the previous iteration. And then we will calculate, or keep solving this until Rn and Rn minus 1 are equal, right? The one thing to take into account or to note is that during during the first iteration, this Rn minus 1 is 0. Therefore, this entire sort of sum equates to 0. So therefore, the first iteration is just the execution time of the current task, right? So we'll do an example of this, and we'll see how this is performed. But hopefully, it makes sense why we're doing this. We want to sort of reach this steady state for each task, and therefore, if we get this sort of steady state response time, then we can just check this steady state response time against the deadline of the current task, and if the steady state response time is less than or equal to the deadline, then the task is schedulable. So that one individual task. But if we perform this check for all tasks in our task set, we can then guarantee that our task is schedulable, because if all tasks meet their deadlines, then of course we're schedulable, right? And so this is exactly what this last sort of line here. So quickly before we finish up with the sort of the scheduling topic, we've been looking really at sort of tasks that run independently of each other. And so the scheduling analysis, you can imagine there's all these different policies, complex systems, and other factors that are really play an important role in doing these analysis. And so like a lot of this falls outside of the scope of this course. I mean, you could do entire courses on scheduling analysis, but for us, I sort of just want to mention the things that are also important to know, and also things that we'll see more in a practical application as we go into like the next lecture on real-time operating systems, and also the sort of the practical component of the course that goes along with this topic. There are some important things that I want to sort of bring to your attention. And like starting off, the first sort of important thing is that we're assuming here in all of these, like what we see in this lecture, that we have these tasks that sort of execute based on their execution times, their periods, and their deadlines, but they don't actually take into account sort of the dependencies, like the data dependencies that they might have on other tasks, meaning that other tasks might actually be very important in them achieving successful execution. And so therefore we have to sort of take into account synchronization of these tasks like mutexes and semaphores, which will be presented in tomorrow's lecture, such that we can actually sort of bring in these constraints or these dependencies into our schedulability analysis, right? And then this sort of plays a role in priority inheritance, which is something we'll also talk about tomorrow, in that these dependencies, these synchronization dependencies, might actually they play an important role when it sort of talks about the priority of these sort of the resources that these tasks might be using, because the priority of these resources, or the tasks obtaining these resources, can actually have effects on sort of the preemption of systems. And so as I've seen here, like priority inheritance, just to read off a definition of it, is that low priority tasks might have exclusive access to shared resources, that temporarily inherits a high priority task from obtaining access to this resource. And so this way we sort of we'll see this tomorrow. This is also like a topic where I'll spend at least 5 or 10 minutes talking about, and I don't really want to overwhelm you with it now. But one also problem that we can then sort of get into from this sort of dealing with synchronization, where tasks actually have dependencies from other tasks, and the completion of other tasks plays a role in their completion. Then you can imagine that you have sort of these problems where you can have what is known as a deadlock, and this is where two tasks are both sort of waiting on another resource that is currently being held by another task. And they're both waiting on each other, and so we sort of enter this perpetual waiting, which is known as a deadlock, right? And lastly, we'll quickly, very briefly, talk about sort of this sort of decentralized scheduling, meaning that you imagine that this is very common in communication protocols, that you have lots of separate entities that run on different systems, like you have a lot of computers running over Ethernet or a CAN bus in like a car or something, and these sort of events and these tasks actually need to communicate over a shared medium, over the network bus. And then we need to then somehow distribute this scheduling protocol such that we can actually use this shared resource, this shared medium, such that these senders don't actually interfere and corrupt each other's transmissions. And so this can be sort of common in, for instance, like Ethernet, which uses what's called carrier sense multiple access collision detection, in where the participants actually listen to see if there's a collision on the network, and if there is, they stop transmitting, and then they just retransmit after they have some sort of a random back-off period. And the back-off period is where they sort of say, okay, I'm going to randomly generate a period of time for me to wait, and then they wait that time and try and retransmit. And if they have another collision, they sort of just repeat this problem. And so this is the sort of the carrier sense, meaning this sort of they can sense activity, and there's multiple access, meaning they sort of they back off and allow for others to use the medium. So similarly, we have CAN bus, which is probably you haven't really had much exposure to. It's very much an industry protocol used, for instance, in cars, and this also implements a sort of a similar thing, but they just does collision avoidance, where the messages attempt to actually sort of detect the possible detect possible collisions by having a preamble. Instead of just sort of detecting the collision, they try to avoid it, and so they'll use a preamble to detect if there's a preamble has been corrupted, and if it has been, this means okay, the message would also get corrupted, and so we're going to avoid sending it now. And so that, for instance, they'll check firstly for an uncorrupted preamble, and then they'll continue the transmission. Right? And so these are a couple of little things that are sort of apparent in this decentralized scheduling, how you would best manage sending transmissions, such that you don't actually collide with the other whatever systems on the network. So that's the end of the scheduling. I'll do a couple of examples of this scheduling analysis, namely, or most specifically, the fixed point computation, to hopefully try and clear up a little bit of how this sort of steady state is calculated and achieved.